Essen, I see Duisburg.
Yeah, you see, you know.
And you will be colleagues now.
Essen, I see Duisburg.
Good.
I saw you had a new opening.
Correct. Replacement for the old guys. Okay. Maybe we start in a minute. I think that's the time, I think, yeah. Okay. So welcome everybody. Let me begin. I think we have hit the time. So welcome back to the online SPICE on SPIN+X seminar series, organized by myself here, together with Angela Wittmann, which is a new scientific coordinator in our team in SPICE, and Karin Eversos-Sitte, who is now a WT professor in Duisburg, and in collaboration with the SPIN+X Research Center led by Martina Schliemann, and Burkhard Hillebrands in Kaiserslautern and Matthias Chloe in Mainz. As you know, this is 3 p.m. seminars, so please check out the schedule for the next few seminars that we have. Whenever there's a conflict with a particular conference, international conference, we don't hold a seminar just to not conflict with it. And today it's my pleasure to welcome some young blood in our field, Christian Tzschaschel. I'm sorry for mispronouncing it very much, but he graduated from ETH Zurich and did fantastic work, so much that he is a postdoctoral fellow at Harvard University looking at optical responses in topological quantum materials, and having had some very nice impact in the last year or so. And this is why we'd like to hear from him. So please go ahead and share your screen, Christian, and start your talk whenever you like. Okay, great, excellent, you can see it.
Yes, thank you. And thank you so much also for the opportunity to present my work in this seminar series. And yes, today I want to tell you a bit how we can maybe use optical laser pulses to excite and probe spin dynamics in antiferromagnets, and we are going in particular to look at coherent spin dynamics in these kinds of systems. And yes, while it's true that I am currently at Harvard University in the group of Suyang Xu, working towards topological materials, most of the work that I'm going to present to you today was done at ETH Zurich in Switzerland in the group of Manfred Fiebig, and in very close collaboration with Takuya Sato, who was at Tokyo Institute of Technology and in Japan, and Shovan Pal, who is now at the National Institute for Science Education and Research in India, and just started there in assistant professorship. And I also want to acknowledge the funding sources, in particular from the Swiss National Science Foundation, but also from Harvard University. Now, the motivation to study antiferromagnetic materials comes a bit from information technology, for instance. So nowadays, the vast majority of data are still stored in the form of magnetic memories. Here we're looking in particular at large-scale applications like data centers around the globe. And in those magnetic memories, bits are encoded as areas with opposite magnetization that encode the zeros and ones of our data. And of course, the magnetization can be switched by the application of a magnetic field between the two states. But this process is actually not quite ideal in the sense that it takes some energy. We need to pass a current through some coil that will generate heat. There's dissipation. The process is also not terribly fast. Could be maybe a bit faster. But the energy aspect is really something worth considering, because it is expected that the data centers around the globe account by 2030 for like 7–8% of the total global energy demand. And that is clearly somehow not sustainable, and therefore people are looking a bit for alternative options. And one option to advance information technology would be to transition from ferromagnetic materials, where we have a magnetization as an order parameter that encodes the information, and transition towards antiferromagnetic materials, where we can then have an antiferromagnetic order parameter. And the materials that we are particularly interested in here are fully compensated antiferromagnets, and antiferromagnetic order parameter in general can be very complicated, but for two sublattice antiferromagnet, common convention is to look at the difference between the sublattice magnetizations. And then again, we can define two states with opposite order parameters that could potentially encode our information. And it was already realized by Louis Néel in 1970 that these antiferromagnets could be potentially very interesting from a theoretical point of view, but he believed that they do not seem to have any application. But that changed a bit recently when people realized that because those antiferromagnets are fully compensated, they are actually robust against externally applied magnetic fields. And at the same time, they're also abundant. Antiferromagnetic materials are quite common. In fact, antiferromagnetism is compatible with all point groups, whereas ferromagnetism requires the explicit breaking of time reversal symmetry. They're also versatile, like many functionalities could be realized in antiferromagnetic devices, not just as data storages, but also some processing. And what is probably most important for the purpose of this talk is that they are fast. The dynamics are expected somewhere in the terahertz regime, whereas ferromagnetic materials, we are looking typically at gigahertz frequencies. And so nowadays, antiferromagnets are envisaged for a whole new class of logic devices. But the problem that we still have, one of the problems is that we want to be able to somehow control an antiferromagnetic state. The question is, how can we go from one of the antiferromagnetic states to the opposite one? And naively, there are at least two different ways how one could do this, simply by rotating the sublattice magnetizations 180 degrees. And you can rotate the sublattice magnetizations both in opposite-handedness, one clockwise, one counterclockwise, or you can rotate them both in a clockwise way. And that there are some differences between these approaches, but it's not quite clear how to manipulate an antiferromagnet in the first place. So for this talk, we are actually not going to focus on antiferromagnetic switching, but we are going to just try to induce a small angle excitation, an antiferromagnetic spin precession, where we can act on the spins and just induce a small canting in either way, as shown here. So there are essentially then three questions that also kind of form the outline of this talk. That is, first of all, how can we excite an antiferromagnet? And this question will be the main part of the talk. Then also, once we have excited some antiferromagnetic dynamics, it would be important to, of course, probe the antiferromagnetic order parameter. And then as a last question, a bit of an outlook, what's next? It's a bit of an open question, like how can we use then our newly obtained capabilities of exciting and probing antiferromagnets for future developments. Okay, let's turn towards the first question. How can we excite an antiferromagnet? And well, if we come back to basically the previous picture where we have the magnetic system in an equilibrium state and in an excited state, it's precesses with some frequency omega and some lifetime tau, then the two ways of canting the spins that I showed earlier, they represent actually a canting where a net magnetization occurs in this fully compensated antiferromagnet, but the antiferromagnetic order parameter, the difference between the sublattice magnetizations, remains vertical. And in the other case, the spins are canted in such a way that the overall structure is always fully compensated, irrespective of the canting angle, but the antiferromagnetic order parameter is rotated away from its easy axis, from its ground state direction. And at this point, it's maybe interesting to draw an analogy to a more mechanistic system, where we can also have a particle in a parabolic potential. In an equilibrium, it just sits somewhere in its equilibrium position in the ground state. So think of it, for instance, as a mass on a spring. And in the excited state, the mass will oscillate back and forth with some frequency omega and some lifetime tau. And also in this mechanistic analogy, there are essentially two ways how to go from an equilibrium state to the excited state, which is either by a displacive excitation, take the particle, put it in a different location where the potential energy is higher, and then release it, or we can kick the particle, transfer some momentum, and also actually keep it at first in the position where it is in the ground state position. And just by looking at the excited state, frequency, and lifetime, those two excitation mechanisms are actually indistinguishable. But the differences show up if we were to follow, for instance, the position of the particle as a function of time, where in one case, the particle is immediately displaced and then oscillates back to its equilibrium position, whereas in the other case, for the impulsive excitation, it starts from the equilibrium position and then oscillates back to its equilibrium position. So in other words, in one case, we have a cosine-like time dependence, and in the other case, we expect a sine-like time dependence. Now coming back to antiferromagnetic spin precessions, we expect dynamics somewhere in the terahertz range. So picosecond dynamics or sub-picosecond dynamics. And to resolve those in time, we will need an optical setup, particularly an optical pump probe setup. And I'm showing here circularly polarized pump pulses and linearly polarized probe pulses, but those are arbitrary, so we can change the polarization to whichever way we want. We will always measure in transmission. The sample will always be a fully compensated antiferromagnet in this talk, at least in the ground state. And what is a bit special in our system is that we have a dichroic mirror after the sample, and we can use then a Wollaston prism and a Bollins photodiode to study the linear optical response, that is, for instance, Faraday rotation or magnetic linear birefringence, or we can look at the second harmonic generation of the sample. And that will become interesting later. But now the first question is actually how the pump pulse can interact with our antiferromagnetic material such that we can induce some antiferromagnetic dynamics. And for this, I want to briefly introduce the inverse magneto-optical effects, and I'm going to show some equations, but it will be quite understandable, so please bear with me. And if we just consider a rather generic free energy density of a magnetic system, there could be some anisotropy term that is quadratic in the magnetic order parameter and some anisotropy coupling constant. There could be some Zeeman interaction that couples the magnetization to an externally applied magnetic field. And the actual light-matter interaction is described by this last term with the electric field of the light E here. And the material properties are encoded in this dielectric susceptibility tensor. And in this case, we already expanded the dielectric susceptibility tensor up to second order in the magnetic order parameter. And then usually the first term gives rise to, for instance, the Faraday rotation, Faraday effect, or magnetic circular birefringence, whereas the second term gives rise to the Coton-Mouton effect or magnetic linear birefringence, which both change the optical properties of the material. Now, to understand the nature of the inverse magneto-optical effects, it's actually sufficient to simply rearrange those terms in the free energy. And we can see that the term that gives rise to the Faraday effect, that is linear in M, we can combine that with the Zeeman interaction in such a way that the laser pulse in the material essentially contributes to an effective magnetic field in the material. And this optically induced effective magnetic field is exactly the inverse Faraday effect. And similarly, we can take the term that is quadratic in the magnetization, combine it with the anisotropy term, and see that in the presence of the laser pulse, the magnetic anisotropy of the system can be modulated. And once we have that, we can go ahead and define the effective magnetic field in the usual way as the partial derivative of the free energy density with respect to the magnetic order parameter. And we see that there will be terms remaining that are proportional to essentially the laser pulse intensity. So this is exactly our optomagnetic field pulse that is only present for the laser pulse duration itself. And with this effective magnetic field, we can then plug this into the Tzschaschel-Gilbert equation and solve how the effective magnetic field pulse affects the magnetization in the material or the magnetic order parameter. So I'm just writing here M, but essentially there are such terms for all sublattices if we have a multi-sublattice antiferromagnet. And especially in the case of a laser pulse that is much shorter than any antiferromagnetic spin precession, which is the usual case, we can approximate this as a delta function in time, and then even solve the Tzschaschel-Gilbert equation analytically. Now, a common approximation that many people do is to neglect the damping term. The argument here is that the Gilbert damping parameter alpha is usually much smaller than 1. So in magnitude, the damping term is much smaller than the field torque, the first torque, and therefore seemingly negligible. We will see later if this approximation is always justified, or maybe there are cases where this is actually not the case. Okay, but let's first study just look at the field-like torque. At this point, this is all just theory, and we now went ahead and tested this theory in an actual material, namely antiferromagnetic nickel oxide. It's a textbook antiferromagnet, really. It has a very high ordering temperature. Most of the experiments were done at 70 Kelvin, so we have a very stable antiferromagnetic order, which is fully compensated. It's a 2-sublattice antiferromagnet, and as there are 2 sublattices, there are then also 2 antiferromagnetic precession modes. And according to our theory of how we can optically excite spin precessions, we find that with the circularly polarized laser pulses, we can excite this in-plane mode, it's called so-called in-plane mode via the inverse Faraday effect. Using linearly polarized laser pulses, we can excite the same mode using the inverse Coulomb-Mouton effect. For the out-of-plane mode, that's the higher frequency one, both circularly polarized and linearly polarized laser pulses excite this spin precession via the inverse Coulomb-Mouton effect. Now, the in-plane mode is actually the more interesting one, or could be more interesting, because it allows us to compare the excitation via the inverse Faraday effect and via the inverse Coulomb-Mouton effect, even in a quantitative way, because it's the same mode that we excite. And this is then the experimental results. We are probing here the magnetic linear birefringence in the system, which is related to the change in the antiferromagnetic order parameter. And we see that if we use circularly polarized light via the inverse Faraday effect, we see a cosine-like time dependence, meaning that the antiferromagnetic order is immediately changed during the excitation via the inverse Faraday effect. In contrast, if we use linearly polarized laser pulses to excite the same spin precession via the inverse Coulomb-Mouton effect, we find a sine-like time dependence, meaning the antiferromagnetic order at t = 0 is actually unchanged. And what happens here is exactly the experimental realization of what I showed earlier, that with the inverse Faraday effect, we rotate the spins in such a way that the antiferromagnetic order is immediately changed, but no net magnetization is induced. The inverse Coulomb-Mouton effect cancels the spins in such a way that there is a net magnetization occurring, which we don't probe here in this experiment, but the antiferromagnetic order remains vertical, remains unchanged. So this is exactly the experimental realization of those 2 excitation mechanisms. Now, more quantitatively, if we look at the amplitude of what is, how strong the response is, and we note that actually the energy transfer, the energy that is carried by the antiferromagnetic spin precession, scales quadratically with the amplitude. We find that the excitation via the inverse Coulomb-Mouton effect is 3 orders of magnitude more efficient than via the inverse Faraday effect. And that is a bit surprising, because the inverse Coulomb-Mouton effect actually arises as a higher order process. If we remember the expansion of the dielectric susceptibility, this is a second order process, whereas the inverse Faraday effect is linear in the magnetic order parameter. So naively, one would expect that the inverse Faraday effect is dominating. And to understand why this is the case, why the inverse Coulomb-Mouton effect is so efficient, it is important to realize a qualitative difference between ferromagnetic and antiferromagnetic spin precessions. So for ferromagnetic spin precession, the magnetic moments during the precession are actually always parallel at all times. So the exchange, the ferromagnetic exchange interaction between the spins is always satisfied. And what determines the precession orbit is essentially just the magnetic anisotropy. So during the spin precession, if we consider damping, if we ignore damping for a moment, the spins precess along a constant energy contour in the free energy landscape, and the energy above the ground state is essentially just this, can be expressed in such a way, which is the equation of a circle, leading to an almost circular motion for ferromagnetic spin precessions. This is vastly different in the case of an antiferromagnetic spin precession, where spins are not always parallel. And in fact, during the spin precession, a ferromagnetic canting occurs, and that frustrates the exchange interaction. Therefore, the exchange interaction contributes to the energy that is carried by the antiferromagnetic spin precession. And this energy, this exchange energy, is usually much, much stronger than the anisotropy energy, leading to a very asymmetric, in some sense, energy landscape, where a canting along a ferromagnetic canting raises the energy much faster than an antiferromagnetic canting. This leads for an antiferromagnetic spin precession to a strongly elliptical trajectory, where a spin canting along the direction where the antiferromagnetic order is modulated is usually much larger than the spin canting along the direction where ferromagnetic canting occurs. And how is that now related to the actual excitation mechanism? Well, as I said before, the inverse Faraday effect and the inverse Coulomb effect cant the spins in different ways. And what is remarkable here is that for an ultrafast optical excitation, if you apply an optomagnetic field pulse, the spin canting is actually independent of the exchange or anisotropy parameters. And numbers work out in such a way that if you apply a 1 Tesla optical field pulse for 100 femtoseconds, the spins will always be canted by 1 degree, no matter the exchange or the anisotropy energy. So that means that a 1 degree canting along a ferromagnetic way will put the system into a way higher energy state than a 1 degree canting in an antiferromagnetic manner. And this is the reason why the inverse Coulomb effect is so much more efficient in the way of exciting a spin precession. Now, this also actually has some important implications to this approximation that we did earlier, where we ignored the damping-like torque. Because if we come back to just to the inverse Faraday effect, we consider some fully compensated antiferromagnet. I show here 3 sublattices, but same thing works also if there are only 2. And we have the effective magnetic field of the inverse Faraday effect, which is the same field then on all 3 spins. Then those 3 spins, the field torque will cant all these 3 spins with the same handedness in such a way that the antiferromagnetic order is perturbed, but no net magnetization occurs. In contrast, if we were to consider the damping torque of the inverse Faraday effect, actually that one would act in the same way for all 3 spins and would induce a net magnetization in the system. And now numerically, the damping torque may be much smaller than the field torque, but as we've just seen, because of the strong ellipticity of the antiferromagnetic spin precession, even this small torque can actually carry or transfer a lot of energy. Now, in an experimental setup, the question is, of course, can we observe this damping torque? How would it show up? And this is again actually quite interesting. So if you just consider the field torque for a moment, then there's no net magnetization. During the spin precession, positive magnetization occurs, goes back to 0, goes negative, goes back to 0. So if we were to follow the oscillating magnetization during the spin precession, we would find a sign-like time dependence. If we consider the damping torque, there will be a finite magnetization immediately after the excitation. Therefore, the initial phase of the spin precession will be affected. It will not be a perfect sine wave. And so let's have a look at the real experiment. This is a typical antiferromagnetic spin precession, actually a very nice one. And we do probe here the Faraday rotation. So that is the oscillating net magnetization that is out of plane of the system. And we can fit the oscillatory part at positive times very nicely with the damped sine wave that gives us the frequency and the lifetime of the spin precession. And having such a very nice quality of a fit, we can then also extrapolate the fit back to 0, to the time of the temporal overlap. And we do find indeed that the fit does not cross 0 at 0 time, but there is a finite initial phase. Or another way to read this graph is to say that at 0 time, there is already a finite magnetization in the system. Now you might say, okay, the effect is quite small. Oh no, wait, so this actually gives us 2 ways now to determine the Gilbert damping parameter. If this model was true, we could, on the one hand, extract it in the usual way from the lifetime of the spin precession, or we could study the initial phase and extract independently from the lifetime, actually, the Gilbert damping parameter from the initial phase. Now you would say, okay, this effect is maybe quite small. It's clearly within the time of the temporal overlap. So to show that those 2 are actually related, it would be desirable to be able to tune the Gilbert damping parameter. And for that, nickel oxide is actually not an ideal system, because you could expect that the Gilbert damping is maybe changed in the vicinity of magnetic phase transitions. And the nickel oxide has its antiferromagnetic phase transition at more than 500 Kelvin, which is in our experimental setup inaccessible. So therefore, we study a system that has phase transitions at a lower temperature, which is the family of the hexagonal rare earth manganites. They have a triangular lattice structure of manganese atoms. Those are the important ones for the magnetism that we want to consider. There are some rare earth ions. And in the system, there is a spin precession that preserves the threefold rotational symmetry of the lattice and exhibits an oscillating net magnetization along the z direction, in the out of plane direction. And we are going to study in particular this spin precession. Yes. What is also interesting about the rare earth manganites is that depending on the rare earth ion, there are different phase transitions in the system. So we always have the nail temperature somewhere around 70 Kelvin. But for instance, for holmium manganite, there is a spin reorientation transition at 33 Kelvin. And yttrium manganite, for instance, does not have that phase transition. At low temperatures, we assume this, but the system assumes this 3 in, 3 out kind of spin configuration that is also shown on the left-hand side. At intermediate temperatures, the spins rotate 90 degrees to a 3 clockwise, 3 counterclockwise spin arrangement. But also this order has a similar Magnon mode, or the same actually, that exhibits an oscillating net magnetization along the z-axis and preserves the threefold rotational symmetry. So that's why this mode is particularly suitable. And we can then, we are going to trace this mode in the case of holmium manganite across the spin reorientation transition. So these are the data that we get then. So for each of these data points, there's in the background a time resolved measurement where we follow the spin precession after the excitation. And we measure the frequency, lifetime, and we also extract the initial phase of the spin precession. And the red line is some simple model, what we would expect for the frequency dependence. And we can clearly see the spin reorientation transition as a dip in the precession frequency. What is remarkable now, if you were to solve the equations of motion for an antiferromagnetic spin precessions, we can show that from the frequency and the lifetime, you can extract this A alpha parameter, which is a kind of an exchange enhanced damping, or geometrically A corresponds to the aspect ratio of the elliptical trajectory of the spin precession, or the spin ellipticity, and alpha is the Gilbert damping parameter. And just from the lifetime and the frequency, we can extract this A alpha product, which has a rather complicated temperature dependence. But with some more analysis, we can separate this also into the temperature dependence of the ellipticity and the Gilbert damping itself. What is more important is that also the tangents of the initial phase can be shown that this is also a function of purely this A alpha product. So we can then take the frequency and the lifetime that we measure after the excitation to calculate what would be the expected initial phase at the moment of the excitation. And those are the red data points. And we find a remarkable agreement really in the vicinity of the spin reorientation transition and towards higher temperatures. What happens at lower temperatures is that the Holmium moments begin to order, and that changes the magnetic anisotropy and affects the spin dynamics in a way that is not part of our simpler model. So we are going to ignore that part. But in the vicinity of the spin reorientation transition, we do find a remarkable agreement, which actually shows that what we have here is a spin excitation with via the inverse Faraday effect. What we have also is shown that the damping torque of the inverse Faraday effect can not be neglected. We have shown that the damping that determines the lifetime after the excitation is already active during the moment of the excitation. And it's also worth noting that the tangents of the initial phase, it actually has a physical meaning, and it corresponds to an energy ratio. If we have purely an excitation via the inverse Faraday effect, then it corresponds to the energy ratio of how much energy is transferred into the magnetic system via the damping torque over how much energy is transferred via the field torque of the inverse Faraday effect. So having a tangent of the initial phase that is larger than 1, it implies that the excitation via the damping torque is actually dominating, despite the Gilbert damping parameter alpha still being a lot less than 1. And the reason for this high efficiency of the damping torque is, again, the strongly elliptical spin precession that we usually find in antiferromagnets. So this summarizes concludes the first part. How can we excite antiferromagnetic spin precessions? And what I've shown you is that the magneto-optical effects, the inverse magneto-optical effects, provide some versatile tools to manipulate the magneto-optical, to manipulate the magnetic order in different ways. And what I've also shown you is that excitation mechanisms that manage to induce a net magnetization in an antiferromagnet have a tendency to be a lot more efficient than excitation mechanisms that purely modulate the antiferromagnetic order. Now, once we have this excitation, in the previous case, we then relied on an oscillating net magnetization to probe the antiferromagnetic order. But it would actually be desirable to have a tool that directly probes the antiferromagnetic order parameter. And here, the capabilities of our setups become really useful, where we can combine linear and nonlinear optics, in particular second harmonic generation. Now, why is that interesting? Well, let me first recap what is second harmonic generation. It describes the interaction of two photons at frequency omega in the material, which leads to the emission of one photon at frequency 2 omega. And this process is mediated by this nonlinear optical susceptibility tensor, which includes, or which encodes the symmetry properties of the material at hand. And we are going to study, in this case in particular, hexagonal yttrium-manganite, which has the same magnetic structure that I showed earlier with this 3 in, 3 out kind of spin configuration. And we are actually going to look also at the same spin precession that we studied before, that we can excite via the inverse Faraday effect. Now, what happens is that in the case of the hexagonal manganites, there are components in this tensor that couple to the antiferromagnetic order parameter. And to show that this is indeed the case, we can measure simple temperature dependence and compare the precession frequency of this mode with the total SAG intensity that we get out of the sample. And we see that they show basically the same temperature dependence. And when the Magnum frequency reaches 0, also the SAG intensity essentially reaches 0. Also, the symmetry of the SAG anisotropy reflects exactly the threefold symmetry of the lattice, so that's also good. And this is all as expected. This is just to show that the SAG component, the specific one that we pick here for this experiment, has indeed something to do with the antiferromagnetic order in the material. Now, our setup also allows us then to measure the modulation of the second harmonic generation as a function of time after the excitation. And this is the results, the main results. Let's first look at the upper two plots, which show the Faraday rotation. Again, similar to previous results that I showed. We find, in this case, a sine-like Faraday response, which indicates that at the moment of the excitation, no net magnetization is induced, just the antiferromagnetic order is modulated. The response is also helicity dependent, as is expected for an excitation via the inverse Faraday effect. So that's all good. What is remarkable is that also the second harmonic generation is actually modulated as a function of time. And that is surprising. It's modulated at the same frequency. And we checked the transmission of the sample, also with time resolution. The transmission both at omega and at 2 omega of the sample does not have any oscillatory components. It's basically flat. And so what we have here then is must be a modulation of the chi tensor, the nonlinear optical susceptibility. What is also noteworthy is that the SAG modulation is cosine-like, so it's 90 degrees out of phase with the Faraday rotation, showing that this is not an artifact somehow of the Faraday rotation acting on the second harmonic generation. Now, the question is, how can the chi tensor, the nonlinear optical susceptibility, be modulated by the antiferromagnetic order? And essentially, there are two scenarios that we can imagine. There could be symmetry conserving dynamics, which just change the magnitude of the SAG anisotropy and would lead to a breathing kind of the SAG anisotropy. Or there could be symmetry breaking dynamics, where new components of the chi tensor become allowed transiently during the spin precession because symmetry is reduced. And this would lead to a symmetry change of the SAG anisotropy. And for the specific mode that we are considering here, where the threefold rotational symmetry is always preserved, we could expect, for instance, a rotation of the SAG anisotropy. And to distinguish those two scenarios, it's not sufficient to just sit on one point and measure as a function of time, but we then measure the full SAG anisotropy at various delay times after the excitation, and then fitted the anisotropy to extract the change in amplitude and orientation. And this is what we find. So the amplitude actually follows a single exponential decay, which we would think just reflects some thermalization. The order parameter is a bit reduced after the excitation because there's some slight heating. But more importantly, the orientation of the SAG anisotropy actually follows a cosine-like time dependence, just as we would expect for a modulation of the antiferromagnetic order. And what is also remarkable is that within our experimental resolution, this cosine-like time dependence is actually background free. So if we were to extrapolate this to infinite times, we would go back to 0 degrees or 0 rotation. It's a background free detection of antiferromagnetic spin dynamics. We understand this rotation as an interference phenomenon. There are essentially two extreme cases. In the magnetic ground state, the spins are pointing along some crystallographic X direction, which gives us one kind of SAG anisotropy. And then we can imagine a fully excited state where spins are along the Y direction, 90 degrees rotated, which results in a 30-degree rotated SAG anisotropy. During the spin precession, the spin encloses some angle, alpha, between the X and Y direction, and that allows the interference between those two components. If the complex phase between the tensor components is correct, then we can find a rotation of the SAG anisotropy. And so more specifically, the change in amplitude then that we find just reflects a change in the magnitude of the magnetic order parameter, whereas the change in orientation reflects the spin canting angle denoted by alpha here, and therefore the in-plane spin canting of the in-plane spin canting. So what we achieved here is a separation of thermal and non-thermal spin dynamics by their respective symmetry response. Now we should also not forget that in parallel we are actually still measuring the Faraday rotation of the sample. So now we have two sets of measurements, the second harmonic generation probing the in-plane spin rotation and the Faraday rotation probing the out-of-plane spin canting. So we can now combine those two and reconstruct the antiferromagnetic spin precession in 3 dimensions. We can even quantitatively estimate at least the in-plane and out-of-plane spin canting angles, where we find indeed a strongly elliptical spin precession, as is expected for antiferromagnets. And in this case, it's actually quite interesting to show this elliptical spin precession with the same scale on both axes, where it looks pretty much like a line. So in that sense, any elliptical spin precession that I showed in some kind of illustration earlier is actually a drastic understatement of the elliptical spin precession that you would typically find in a real antiferromagnet. All right, so that concludes the second part of the talk. I hope I could show you that time reversal second harmonic generation provides some interesting insights into the dynamics of the antiferromagnetic order parameter. And most importantly, it allows to directly probe the antiferromagnetic order in a material. So then what's next? Well, at this point, I want to take the opportunity and basically advertise our recently published perspective on non-linearities in coherent magnetization dynamics. And how are those related? Well, it brings us back essentially to the motivation of this talk, that the final goal is to switch the antiferromagnetic order from one state to the other one. And what I've shown you so far is that we have optically the control to Kant spins in whichever way we like, basically, to induce a small angle excitation. But in the kind of intermediate regime between achieving switching and between having a small angle excitation, there lies the nonlinear regime of magnetization dynamics. How comes that about? Well, we can go back to our mechanistic analogy where we had our excited state and a parabolic potential. Now, practically, if we want to switch something, that means that we need to have at least 2 degenerate states in energy, two energetic minima, 2 stable energetic minima. But a single parabolic potential where we observe typically harmonic dynamics can only have 1 minimum. So that means that in a real system, necessarily the energy landscape needs to be more complicated than just a single parabolic potential. That also implies that if we were to crank up the oscillation amplitude, we would necessarily find deviations from the perfect harmonic dynamics. We would find asymmetric dynamics, anharmonicities, and those are hallmarks of nonlinear dynamics, including nonlinear magnetization dynamics. So in that sense, understanding nonlinearities in magnetization dynamics, it directly advances and accelerates the development of potentially new ways for switching and controlling magnetization in a material. Now, the question is how could we potentially amplify the precession amplitude that we can induce? And so far we just relied on a kind of a Raman-like process, actually, where we have 2 photons and some difference frequency generation. And this process, we will need to make this process stronger. And there are ideas, for instance, relying on cavities to enhance light-matter interaction, or there are ideas using terahertz radiation to resonantly excite the spin precession in a 1-photon process. But a way that I find particularly interesting, actually, goes towards phonomagnetism. So we can use those 2 photons to actually excite 2 phonons in the material, let them interact to induce the spin precession. And that this works was actually shown already experimentally, for instance, in this Nature Physics paper. But there are also interesting theoretical predictions by Dominik Juraszek and co-workers showing that this should be actually way more efficient than the direct optical excitation. And I should also say that these pictograms are actually taken, I think, from the PRB that I cite here. And the point is that by exciting these phonons in between, we circumvent a problem of the direct optical excitation, which is that the effective magnetic field pulse, the optomagnetic field pulse, occurs on a much shorter time scale than the typical magnetization precession frequency. Therefore, in frequency, there's a rather poor spectral overlap between the excitation and the resonance that we want to excite, making the whole excitation process rather inefficient. And by exciting these phonons in between, we basically can extend the excitation process to a time scale that is closer to a typical time scale of spin dynamics, including antiferromagnetic spin dynamics. And that can improve the efficiency of the excitation. Also, it is shown in these theoretical works that actually the effective magnetic field amplitudes that are achievable can be way higher for these phononically generated magnetic fields. And in this case, it's also noteworthy to remember, for instance, last week's seminar talk by Andrei Kyrylyuk, where he showed some preliminary results that this phonomagnetic couplings, or the phononic analog of the inverse Faraday effect practically, they managed to switch the magnetization in a ferromagnet, which is very exciting actually, and shows that it is indeed possible to induce large changes via this phononic coupling. And similarly, in this theoretical works, it's predicted that there should be also a phononic analog of the inverse Cotter-Mouton effect, which I believe at least should be very efficient in exciting antiferromagnetic spin dynamics. Going a bit in a different direction, we can also try to make the dynamics faster. There's more to explore in antiferromagnetic spin dynamics. And at very ultra-fast timescales, there are ideas to extend the Lanois-Schütz-Gilbert equation and induce, for instance, include, for instance, inertial torques which could give rise to the ultra-fast excitation of mutations on timescales of 100 femtoseconds or maybe even less, which opens up a rather completely new field of antiferromagnetic spin dynamics. And another direction that we kind of discuss in this, in our perspective, is to look at weirder dynamics in some sense. So because so far we looked at systems that actually order magnetically or antiferromagnetically. But if we consider also frustrated magnetism or some emerging magnetism due to topology, the order is actually not important anymore. Or it may even happen that due to frustration, the system never orders at all. And the ultra-fast dynamics on such systems are completely unexplored, but also in some sense closely related to antiferromagnets, because it's particularly in the example of this triangular lattice, you need antiferromagnetic exchange interactions to even have some frustration. So those are some very interesting directions that we foresee and discuss in this recent publication. And with this, I would like to conclude actually. I hope I could show you that ultra-fast laser pulses can efficiently excite spin dynamics in antiferromagnets. Here I want to reiterate that the initial phase, although maybe sometimes being a bit of an overlooked measurement parameter, it can provide some very valuable information about the excitation mechanism. And the strong ellipticity of antiferromagnetic spin precessions can facilitate completely new pathways for excitations that are unavailable to ferromagnets. In particular, we saw that any excitation mechanism that manages to induce a net magnetization in an antiferromagnet will be very efficient in exciting an antiferromagnetic spin precession. I further showed you that nonlinear optics provide a powerful probe of antiferromagnetic spin dynamics. In particular, the combination of linear and nonlinear optics enables a full reconstruction and the tracking of the antiferromagnetic order parameter in 3 dimensions. But with those tools established, it's basically just the starting point, and there are many more things to explore in antiferromagnetic dynamics, fundamentally new magnetization dynamics that can occur, for instance, in the nonlinear regime of antiferromagnetic dynamics, or dynamics that involve emerging concepts such as topology or spin frustration. And with this, I would like to thank you for your attention.
Thank you very much. Applause there as well. Very exciting work, and that's very, very clear actually. So now the talk is open for questions. Please raise your hand or write your questions in the Q&A. We'll begin with Thomas. Thomas, can you please go ahead and ask your question and unmute yourself? Yeah.
Thank you very much for the talk. I kind of missed this argument why, in the case of inverse Cotter-Mouton effect, you get an impulsive drive, not displacive. Could you maybe repeat this argument.
Okay, so it depends really, actually, in my point of view. So for this mechanical system, we typically make a distinction between displacive and impulsive excitations, because it feels more natural to live in a real world, and then changing the position will be considered a displacive excitation. But actually, for an antiferromagnetic spin precession, this the change in magnetization and the change in antiferromagnetic order are also canonically conjugated variables, and it's kind of arbitrary which one you consider analogous to the position and which one you consider analogous to the momentum. So then the assignment of what is impulsive and what is displacive is not really unique in that sense. So if we look at the study something that probes the antiferromagnetic order, then the inverse Faraday effect has an impulsive excitation and has a displacive effect on the antiferromagnetic order, and the inverse Cotter-Motor effect has an impulsive effect. Whereas if we were to look at the net magnetization, which is induced by the inverse Cotter-Motor effect, then the magnetization is displaced and the antiferromagnetic order is impulsively excited. So at least in my understanding, this assignment of what is impulsive and what is displacive is not really unique for antiferromagnetic spin precessions.
Yeah, but one is related to potential, let's say, energy, one is related to kinetic energy. And they kind of, I mean, I would like to understand that better. I don't understand, I admit.
I think also the assignment of potential and kinetic, it comes again from the analogy to the mechanistic system. But in this case, it's more magnetic anisotropy and exchange interaction. And so which one of those do we consider as a kinetic energy? I think this is arbitrary.
Maybe you guys can see more afterwards. So first, we're going to go first Martin, then Alireza, then we have all the written. So go ahead, Martin, your question, please.
Thanks very much for a very interesting talk. I have just two short questions. One is, do you know how strongly you heat the lattice transiently with your laser pulses? And the second question is, why you use an IR laser to pump? What is the fundamental reason of it?
Well, why do I use an IR reason for what?
To pump 0.97 electron volt, not let's say something in the visible region or something.
Okay, yeah. So those two questions are actually related. We are using a near-infrared laser pulses to stay below the band gap of our antiferromagnets that we study. Those are semiconductors, and we try to excite them below the band gap exactly with the purpose to avoid heating effects. And we can see some signatures of lattice heating, but the excitation mechanism is designed in a way that we minimize the effect of heating. We don't really want to have that. Although I should admit that, especially in the time-resolved SHG measurements, we do see that there is some thermalization behavior that is probably related to heating of the lattice. We did not quantify that, but most of the laser beam is really transmitted, so we don't expect a heating of more than a few Kelvin.
Okay, thanks.
So Alireza, can you go ahead and ask a question?
Thank you. I have a basic question about the inverse Faraday effect and inverse Cotter-Motor effect. In conducting systems, we understand inverse Faraday effect based on spin-orbit coupling, electronic spin-orbit coupling. I'm wondering in nickel oxide, how microscopically we can define or understand the inverse Faraday effect?
That is a very good question, and one that I have not too carefully thought about, because for me these effects are, I only consider them on a phenomenological level. We can define these couplings and then the effects drop out. If you want to look into the microscopy, we should probably look at what kind of electronic transitions occur near the pump energy. And I think it was there is a work by David Bossini who, and co-workers who showed that, especially in the case for nickel oxide, at the pump wavelengths that is usually used, there is a, I think it's a Magnon sideband of some resonance. And
because also there is another mechanism that I think the Rosin group usually explore, in which you change exchange coupling somehow by laser pulse. And then this is not inverse Faraday effect. Yeah, this is just change.
Yes, the change of exchange interaction would be something else.
That's yeah, okay. Yeah, thank you.
Yes.
Okay. So let's maybe Amir, I don't know if you're able to talk, or maybe I can ask a question for you, Amir. Okay, he's not muted, so maybe I'll read the question. He's written it on the chat in Q&A. So thank you for that very nice talk. Would it be possible to conduct similar measurements in a reflective geometry and Kerr effect, particularly rather than the transmission, to look at opaque samples? And furthermore, what are the requirements that for the balanced diode in order to map the ultrafast process? Okay, that's a very interesting question. And I do not see a reason why similar measurements should not be could not be conducted in a reflection geometry. And I think people have done that even to measure time-resolved MOG as a probe of an oscillating net magnetization. And there are also actually no specific requirements for the balanced photodiode. It should, of course, be able to detect the near-infrared laser pulse that we use as a probe. But it does not need to be particularly fast. It's the balanced photodiode that we use as a commercial one. There's nothing special about it. Okay. So Helen, can you please ask your questions?
Yeah, thank you. Thank you. Very interesting talk. But I will ask maybe a very similar question as Tomasz did. Can you go to this slide where you show delta L and delta M excitations?
Like this one, for
instance?
Yeah.
So in antiferromagnets, we usually consider any dynamics in framework of this delta M excitation, as long as we assume that the sublattice magnetization is constant. So I do not fully understand what you mean by delta L. Does it mean that the L vector rotates in space, or you are talking about oscillations of the antiferromagnetic vector's lengths?
No, I'm talking about a rotation of the antiferromagnetic vector.
Yes. Okay, then yeah, thank you. And concerning the inverse Faraday effect, so again, I think that you were also co-author of the paper with Ivanov, where they showed this that inverse Faraday effect is in antiferromagnets is a second order effect, so it's proportional to the intensity. So by circular polarized light, you create effective magnetic field which oscillates and couples with the antiferromagnetic dynamics. Is it the same inverse Faraday effect, or it's something different? Because when I look at the formula, they look a little bit different.
I think it should be the same inverse Faraday effect. It's maybe
so it should be proportional to the intensity of light.
Yes.
Okay, thank you.
Okay, So let's go next to Massimo. It's been waiting. Massimo, go ahead.
Thank you. Thank you. The physics is really fantastic in this talk. But going back to your original statement about the motivation for, improving memories and things like that, the nice things, I mean, the ferromagnets have all the negative aspects that you pointed out, but they are easily digital, right? The spin is up, the spin is down, the magnetization is there, the magnetization is not there. It's a 0-1 thing. All the stuff you presented today, at least to my mind, looks definitely analogic, right? You have a continuous variable, you have this precession of things in a, the things which are real numbers, not integers number. How do you possibly envisage a digitization of this kind of information storage?
Well, okay, that's also very interesting questions. Coming back to the applications. So first of all, the data storage is one of the possible applications, and maybe we can also think of applications of antiferromagnetic materials that can actually make use of more continuous variables. But I think antiferromagnets can also be used for data storage, but then the goal would need to be to really switch the antiferromagnetic order, to go from one antiferromagnetic state to the other one, and use that as a bit, which may not be immediately practical in many systems, because it is of course challenging to distinguish those two states. But at least in certain antiferromagnets, it is possible. For instance, by relying on, say, harmonic generation, you would see that one domain is brighter, or you could see under certain circumstances that one domain is brighter than the other one. So that would encode some kind of bit. Yes, is that a satisfactory answer?
Well, it's not simple to, of course, if you switch the sublattices, the up and the down sublattice, macroscopically, that is very difficult to distinguish. But I think I agree with you. In principle, it's possible to do some experiments that do that.
Yes. So the whole
straightforward.
Yeah, the whole purpose of this talk was to introduce these ways how to act on an antiferromagnet on ultrafast timescales, and just to induce a small perturbation. To actually switch something is a whole different challenge. Actually, to be honest, for the purpose of applications, the 180-degree switching that I showed here is not even necessary, but we could also consider a 90-degree switching, which is way easier to read out also. Yeah.
Okay, thanks.
Okay, so we go first Davide first, and then Goss afterwards.
Hi, everybody. Thanks a lot for the talk. I would like to join the discussion about the point raised by Ali Reza. So because Christian mentioned our work, in general, what was presented as inverse Faraday effect microscopically is understood as Raman scattering of magnons. And in the case of these low energy magnons, the magnetic interaction responsible for that is a spin orbit coupling. So in when Christian wrote down the energy, this term in this orange box, that tensor microscopically contains the Raman cross-section. And in the case of the modes that Christian discussed today, spin orbit coupling is the relevant thing. As you guys mentioned, when we talk about modifying the exchange, as it is done, it was reported in the Nijmegen group, then we talk about another terms in this energy, in another level. Our work was a bit different because we showed an alternative approach to kick the same magnons via the magnonic sideband. So it was a resonant excitation. But also in that case, the responsible magnetic interaction is mostly spin orbit. Just wanted to point this out.
Okay.
Thank you, and thanks for the talk.
Thank you.
Very good. And then, so please, Sumit, can you ask your question first? No?
Yeah, thank you for this wonderful talk. I have a question about your initial dynamics. Could you comment on what actually happened, let's say, in first 500 femtosecond or 1 picosecond? Because in your picture, I think slide 12, you show this nice curve and give the initial argument, which fits well with the process. But if you look 12, I think.
12.
Yep, this one. But close to 0, the data is really chaotic. So can we say anything about this particular time regime? What is the dominant mechanism of absorbing energy and reorganizing the angular momentum in this case?
Okay, yeah. So in this regime, very close to the time of the temporal overlap, you get basically interactions between the pump and the probe pulse that change the optical properties. So in that sense, the signal that we are measuring here is not necessarily related to the magnetization dynamics anymore. And we neglect that part of the data and only use the part where we have a nice oscillation to understand the magnetization dynamics, and then extrapolate back to t equals 0, to the time of the moment of the excitation.
So I work with theory. So let's say if I want to fit my model or extract some parameter, what kind of data I should look at in this time frame? Because as you say, your measurement would have some interference due to this interaction between pump and probe measurement pulse.
Yeah.
So is there any other thing I can look at this point?
I think in theory, it's isn't it quite simple to just directly look at what is the net magnetization, for instance, of the material, and that should not show this kind of artifacts.
I see. Okay, thank you.
Okay, great. So Igor, can you please ask your question?
Thank you. Thank you for.
Sorry, the volume, Igor, is still low. I think we need to work on that a little bit. And now it's better, yeah.
Can you hear?
Yeah, now it's good.
Okay, thank you. There is an unexpected thing that inverse cotton Newton effect much stronger. And my question is about anisotropy modulation. If there is any data comparing holmium and yttrium compounds. You talked about holmium, and you didn't mention anything about yttrium. You talked about yttrium and didn't tell about holmium.
Yeah. Yes. Okay. Yes, it's true that in particular in this part of the talk, I only showed you the dynamics for holmium manganite. We have the same temperature dependent measurements also for yttrium manganite in this paper. What we see actually is that so we can speculate essentially based on the temperature dependence of the Gilbert damping. We can speculate what is the dominant damping mechanism, and we found that a holmium crystal field excitation could be responsible for the damping. So then when we do the same kind of measurements in yttrium manganite, we find indeed a much longer lifetime and a damping constant that is an order of magnitude lower, which kind of supports this speculation. But overall, the picture in yttrium manganite is very similar. The lower damping than in yttrium manganite allows us to not only study the dynamics around this first order phase transition in the case of holmium manganite, but also closer to the nail temperature as an example of a second order phase transition, and see how the damping behaves there. In particular, we find indications that the damping diverges at the near temperature. Does that answer the question?
Also, I wanted to know if you see directly in second harmonic measurements influence of orbital moment. I mean that in holmium and the yttrium, certainly you have different orbital moment of rare Earth, and it should be somehow seen in measurements. And actually, question is also connected with behavior of this rare Earth, which is sitting in kind of cave surrounded by, exactly, this polyhedra.
Yes.
It can actually show different structure of levels in this surrounding due to existence of orbital moment.
Yeah, so I'm not even sure if there is still an orbital moment, or maybe it is quenched because of the reduced symmetry of the environment of the rare earth ion. But maybe
you are talking about excitations. That's important, right?
Yes, but
you are talking about excitations, and question is whether these excitations show up with the orbital moment or not.
We didn't look into that, and I would say we didn't find a signature of any orbital dynamics. But also, if this is particularly related to the rare earth ion, I would expect the dynamics to become more prominent at lower temperatures, which is the regime that we excluded here.
Okay.
Okay. So
thank you.
Thank you. Last question from Gisela.
So thanks for this nice talk. Excuse me, I have no camera with me. I want to come back to Massimo's questions. Your selling point is that antiferromagnets are ultra fast without external field and so on. But your experiment, I guess, are done on a very large sample with a very large laser spot. So if you sell this as a storage media, you have to compete, you have to go below 100 nanometer, even more. And I haven't got, nevertheless, why you need terahertz, because everything works on gigahertz, but this is only a side statement. So your materials, if you work with these materials, oxides are really harsh to nanostructure and even to prepare as thin layers. Are there any ideas how to solve this problem, or is it, as I believe, unsolvable?
That is a very good question, actually, because it relates back again to the motivation. Whereas this talk was more about the fundamental ways of how can we even begin to think about some applications for antiferromagnets. Okay. So there are now.
Physics is beautiful. I have.
Yes, I understand, and I know now that there are hexagonal rare earth manganite thin films of very high quality. But of course, also that is just one more step towards an actual device, and it's it is a challenge. Maybe there can be some kind of resonator structure to focus the laser beam to a sub-diffraction limit and then modulate antiferromagnetic order on very short timescales. There are, I think, some ideas to excite spin precessions at higher K vectors that would then also correspond to modulations of the antiferromagnetic order on shorter length scales. But all of this is not really practical for like the living room of everyone. But it's there are definitely some research still needs to be done to actually bring this into an ultra fast device.
Okay, thank you.
But Gisela, I mean, maybe I could chime into that because you focus on storage of information. But sometimes here you can also think of, for one of you, of memory stores and artificial intelligence type of hardware devices. You don't really are tied anymore to this small nano devices, but you can also upscale it and still be very efficient. So that can be an area that this could be exciting to do. Yeah.
Also true.
Not just trying to I would say to replace some very established technologies like this. It's not going to be something that's going to happen probably in our lifetime.
Yeah, but if you have a fast way to write, you also want to write a lot. Yeah.
Of course, you cannot have your cake and eat it too many times. I agree with that. Even though we like to say it is, but it's definitely not. But also, I think it's good to think outside the box of the technologies that are not there to be replaced, but to be created. Where there's not that restriction of needing to be at the scale. Yeah.
No, the motivation is excellent. So I know this.
He took the motivation from people that write these things. I mean, the physics is beautiful. Okay, so thank you. I think that's all the questions so far, and thank you for the very active discussions. And Christian, for a beautiful question, beautiful talk with lots of very exciting work. I'm very happy to hear that you're coming back to dear Deutschland to do your work as you should. And we're looking forward to seeing you in Mainz, actually, in a month or so, where you will enjoy some wines in the tasting that I will deliver. So with that, I'm going to stop here the streaming here in